Today we'll do the analysis of AC circuit with all three components, that is inductor, capacitor as well as resistor. When we connect these three components in series with AC signal, then what will be the nature of current in this circuit? We'll try to reach to a point, we'll try to derive the expression for the current in this series LCR circuit, and then we will analyze its nature. So I am spotlighting my notepad. I hope it's visible. Yes. So today's task is AC applied to AC. AC applied to series LCR. This is what we are going to see. So we'll start with the namkaran of the circuit, right? So consider an inductor of inductance L, capacitor of capacitance C,
मोदीले पैसे मागायचे तुला मोदीले
those who are not attending the session, yes, so we have connected an inductor of inductance L, capacitor of capacitance C, resistor of resistance R in series, and this we are connecting to the AC signal with E0 sine of omega t, where E0 is the peak value of voltage. Let I be the instantaneous current flowing through the circuit at any instant small t, at any instant small t. And yes, consider E equal to E0 e to the power j omega t. This is our equation 1. Imaginary part of this equation, that is equation number 1, represents AC signal. Means what does it represent? It represents E0 sine omega t. Right? So E is complex, and this complex is having two terms. One is real term in terms of cos omega t, and other is imaginary terms having sine omega t. So imaginary part of this equation is actually our AC signal that we have applied in the circuit. So this is LCR. We know that this is signal, and now this signal, this voltage will get dropped across L, across C, as well as across R. So applying Kirchhoff's law at any instant t. At t, at any instant t. What we are going to get? E0 e to the power j omega t will be equal to the potential drop across L, that is I times the resistance of L, that is j omega L, plus I times the resistance across C, that will be complex, that is 1 upon j omega C. You can see this, plus I times the resistance across resistor, that is IR. So we can write E0 e to the power j omega t is equal to I times, in the bracket, R plus j, which is common, omega L minus 1 upon omega c. If you can understand this, if you can understand this, how I have written these two terms like this. I have taken j common, I is already common. So in the bracket omega L, if I will take j outside, what does it mean? I will multiply numerator and denominator by j. So numerator will have j and denominator will have j square. That's why minus sign comes into the picture. Then j will be common. So I will get two terms. One is the real term and other is imaginary term. Means this is a complex term for us. So rewriting the same equation as I is equal to E0 e to the power j omega t divided by, I will shift this term here, R plus j omega L minus 1 upon omega c. Right. This is our equation number 2. Now see this, observe this equation number 2. This is equation number 2. So numerator is having E0, that is constant, e to the power j omega t. Denominator is complex number, that is r plus j times omega L minus 1 upon omega c. So this is a complex number. If E0 is the numerator and divided by, so in numerator we have voltage, peak voltage. If it will get divided by resistance, effective resistance, which is nothing but the complex impedance, looks like R plus J times omega L minus 1 upon omega C. So this term R plus J times omega L minus 1 upon omega C represents complex impedance. And we are going to solve this complex impedance in the same manner, in the same fashion that we have adopted for LR circuit and CR circuit. Right? So for us, this is complex term. So now we'll leave this equation 2 here and we'll consider this complex term. And we'll denote this complex term by Z bar, by Z bar. So let us consider Z bar is equal to R plus J omega L minus 1 upon omega C. For us, this is small 1. Small 1. Now this Z bar with us. Also, we'll take the real term as Z cos of phi. This is second, and the second term, that is omega L minus 1 upon omega C as Z sine of phi. Same thing, complex number. Therefore, when we'll square and add, we'll get the value of Z as under root of R square plus omega L minus 1 upon omega C whole square. That is XL minus XC whole square. Omega L is XL and omega C is XC. So this is Z, and the other term we are interested in phi. Phi will be tan inverse of omega L minus 1 upon omega C divided by R. And this is third, this is fourth. And if we'll replace the value of R and omega L minus omega C in equation 1, small 1, then what we are going to get? Also, Z bar can be written as Z cos phi plus Z sin phi. What does it mean? I can represent Z bar as Z e to the power j phi. E to the power j phi. This is equation. So we will put this equation 5 in our equation number 1 for current. Means we will get Z, that is impedance in terms of j phi. Complex impedance in terms of Euler's identity. Right. So put 5 in equation number 2. Put 5 in equation number 2. Yes, Anurag, is there any problem? अनुराग, yes.
यस सर, वहां पे नहीं क्या जे चाहिए, वो जो अल्सो जेड बार इज इक्वल्स टू जे कॉस फाई प्लस जेड कॉस फाई प्लस जे जेड साइन फाई सर लास्ट में.
Yes, it will have. That is for sure. Then only we can apply Euler's identity. Good, thank you. So Z bar is equal to Z times e to the power j phi. These steps are clear? Any doubt? Same thing we are dealing with, right? We are doing same thing, whatever we have done. Karuna, yes?
sir, wait, sir.
Vishakha, you have issue with your mic. Please don't speak. can text.
Sir,
Mute yourself. Yes, Aniket.
sir, your question number is wrong. Means wrong.
One,
You have given
two,
equation number
three.
3
Yes,
twice.
yes, yes. This will be 4. This will be 4. This will be 5, and this will be 6. Thank you. I do mistakes.
सर
Yes.
सर कुछ स्टूडेंट सर ज्वाइन नहीं हो पा रहे हैं, लॉग बता रहे हो.
Yes, I have logged the session. Check this. We were late. Thank you. So this z bar is equal to z times e to the power j5. We will put this in equation number 2 in this equation. So what we are going to get? What we are going to get? I am going to the next page. So we will get I, value of I equal to E0 upon Z e to the power j5 e to the power j omega t. Then what does it mean? I can write I is equal to E0 divided by Z e to the power j omega t minus pi. Therefore, I can write now this is voltage divided by impedance. This can be the peak value of current in the circuit. E to the power j omega t minus pi. This is my equation number 3. This is my equation number 3, right? Where I0 is the peak value of current. And Z represents, Z is the impedance of the circuit. So third equation is the equation which says that current in series LCR circuit, current in series LCR circuit has some phase difference, and this phase difference is given by phi, which is equal to tan inverse of XL minus XC divided by R. XL minus XC divided by R. So what can one conclude from this equation? One can conclude that current lags behind the voltage or current leads the voltage. We have L as well as C in the circuit. Earlier we have seen whenever we deal with L, then current lags behind the voltage. When we deal with pure capacitive circuit or CR circuit, current leads the voltage by some phase angle. But here in this case, we have got the value of phi. We have got the value of phi, which can be positive as well as negative. When phi will be positive, current will current will lag behind the voltage in the circuit. Whenever the value of phi will be negative, then current will lead the voltage in the circuit. And let's check out the play between the value of phi. So now equation 3 can only be concluded with respect to the values of phi. One thing is sure from equation number 3, that current has certain phase difference with voltage. That is for sure. But whether it is leading or lagging behind, it depends on the value of phi, where phi can be positive or can be negative or can be zero also. So we'll see the conditions under which this phi will be positive, negative or zero. And yes, one more thing, that the effective resistance of the circuit is decided by the value of Z, which is nothing but impedance of the circuit. So let us consider the different cases. So here we have case 1. So in case 1, when reactance offered by inductor, that is XL, that is omega L, is greater than the reactance offered by capacitor. Then the value of phi, which is equal to tan inverse XL minus XC divided by R. So this XL, whenever will be greater than XC, the numerator will be positive and denominator is also positive. Then phi will be having positive value. The value of phi will be positive in this case. What does it mean? Phi will be positive. So if phi will be positive, then minus of positive value means current will lag behind the voltage. What does it mean? Current will lag behind the voltage in the circuit. Now consider case 2. Case 2 is whenever XL will be less than that of XC. Then this, yes,
XC ची व्हॅल्यू 1/XC आहे ना?
1 upon XC. XC ची व्हॅल्यू 1 upon XC नाही आहे. XC is equal to 1 upon omega C. मी XL आणि XC
हा तिथे XC च्या जागी 1/XC आहे ना, म्हणजे फॉर्म्युला
1 upon XC नाही आहे, 1 upon omega C आहे. This is XC. XL म्हणजे ओमेगा L, XC म्हणजे 1 upon omega C. इथे व्हॅल्यू पुट नाही केलाय, राईट. XC लिहिलाय. रिएक्टन्स आहे, डिफरन्स इन द रिएक्टन्स डिवाइडेड बाय रेजिस्टन्स. लक्षात ठेवा की XL आणि XC याचं युनिट काय आहे? ओहम. त्याच्या डिफरन्सचं युनिट काय राहणार? ओहम. आणि डिनॉमिनेटर मध्ये काय आहे? रेजिस्टन्स. याचं युनिट काय आहे? ओहम. ओहम डिवाइडेड बाय ओहम. टॅन इनवर्स आपण नंबरचा काढतो. हा एक नंबर राहणार आहे, युनिटलेस नंबर राहणार आहे, राईट. तर XC जर मला इथे लिहायचं असतं तर मी लिहिलं असतं ओमेगा L minus 1 upon omega C. Right, so XC is equal to 1 upon omega C. XC म्हणजे 1 upon XC नाही. Always remember. So when XL will be less than XC, then you can see the numerator will be negative and it will be tan inverse of negative. Tan inverse of negative number is minus of tan inverse of that. right, according to trigonometry, right? So this phi will be negative, and whenever this phi will be negative, negative of negative will become positive. So the phase difference will add, right? And in this case, current will lead. Current will lead the voltage. Simple. Now case 3. Case 3 ahead, whenever XL will be equal to XC. If XL will be equal to XC, means the resistance offered by inductor, when it matches, when it will be equal to the resistance offered by capacitor, means when the reactance value of capacitor and inductor will be equal, then numerator will become 0 in this equation. Phi equal to tan inverse of 0 upon anything will be 0. Tan inverse 0 will be 0.
0.
Tan inverse 0 is 0. Means phi will be equal to 0. What does it mean? Whenever phi will be equal to 0, so in this equation, what you are going to get? I equal to I0 e to the power j omega t. Means there will be no phase difference between current and voltage in this circuit. So circuit will behave like a pure resistive circuit, isn't it? Where there will be no phase difference between current and voltage. Current and voltage will maintain same phase. So here what will happen? Current and voltage will have same phase, and this circuit will behave like a pure resistive circuit. Here in this case, when phi will be negative, here in this case, phi will be positive. Whenever current will lag behind the voltage, so the circuit will behave like inductive circuit. It will be capacitive circuit. And here in this case, it will be resistive circuit. So with series LCR, we can tune the circuit whatever is the requirement. So whenever we deal with L as well as C as well as R, we can have our own choice. If I want the circuit to behave as a pure resistive circuit, then what I will do? I will select the value of XL such that this value should be greater than XC. How can I select the value of L? If suppose I'm using 50 Hertz signal, the choice of L will be there with me. So I will take the combination of omega L such that this product should be greater than that of 1 upon omega C. That of 1 upon omega C. then only the circuit will behave as a inductive circuit. If I want capacitive circuit where current should lead the voltage, if I am fixing the frequency of the signal omega, then I can play with the values of C. But in between, if I want to make the shift, then I need to play with the value of signal. 50 hertz, I can change it to 100 hertz, 60 hertz, or whatsoever. So by playing with the value of omega, we can play with the value of XL and XC. If we want to tune the circuit such that XL is equal to XC, then at what frequency and what values of L and C will give me this combination that we need to understand, right? And under this condition, the circuit resonates. Under this condition, the circuit resonates. Whenever XL will become XC, whenever the value of XL in the circuit becomes equal to the value of XC, the circuit becomes pure resistive. Circuit becomes pure resistive, and this condition is known as resonance condition. This is known as resonance condition, where the amplification takes place. And about resonance, we will discuss in our next session. Now, I invite your inquiries related to this article. We will discuss now.